Okay, we're looking at three dimensions here. We've got two vectors. We want to find the resultant force. We want to find its magnitude and coordinate direction angle. So the first thing we need to do, just like in two dimensions, is write our forces in Cartesian form just by adding that third dimension, that z component. So, of course, F1 only has two components. That's lying in the YZ plane. So the x component is 0. This is just a 2D similar triangle sort of problem. 7/25 in the y. So 7/25 times 630 in the y direction. Okay. And then in the z direction, it's down, so it's negative, and that's 24/25 in the z direction. Okay. And the z direction represents the k direction. Okay. F2, it's given those coordinate direction angles. Okay, so it's just 250 cosine of each one of those. Okay, so going from the x, it's this 60, so cosine 60i. From j, it's 135 from the y, so it's going to be plus 250 cosine 135j plus 250 cosine 60 in the k direction, which again represents this angle from the z down to the angle there. Now, notice that this j is actually pointing in the negative y direction. Cosine of 135 is negative 0.707, so that negative will automatically go in there. So just blindly just positive cosine of all these angles, just recognizing once it goes past 90 degrees on a cosine, then that actually flips to negative there. So just keep that in mind. Now, all we do is we add the x, y, and z components together to get our resultant force, and I get 125I minus 0.377 J is effectively 0 compared to that other value, minus 479.8 K. That is the force written in Cartesian form. I could add pounds here, and I could leave it like this. Now, in three dimensions, I actually prefer it this way. To me, it's easier to draw that vector with those components rather than what the question's asking for, which is the magnitude and the coordinate direction angles. The magnitude is a relevant value, okay? And it's just uses Pythagorean theorem, but for three dimensions, which is still just the square root of the sum of the squares. We just have three components instead of just two. So it's 125 squared plus 3 or 0.377 squared plus 479.8 squared. And that resultant force, that magnitude, is 496 pounds. Okay. Now the coordinate direction angles, which are a little bit more complicated, harder to visualize, I think, than just the three components. But just like above, when we just blindly put cosine, we just blindly use the inverse cosine on this as well. So alpha on this guy is going to be inverse cosine of um, 125 divided by 496. It's just basically the x component over the magnitude. Okay, and that gives me 74.5 degrees. Beta, and I'll draw what these actually are here in a second, is the inverse cosine of negative 0.377. Again, that's the y component of my force divided by the magnitude of the force, which is 496, which gives me 90.04. Okay, and then gamma is going to be the inverse cosine of the z component, which is negative 479.8 divided by the 496, which is the magnitude. And that gives me 165 degrees. Now you tell me, yes, that's the answer, okay, for that resultant force, which would be easier to draw, okay? For me, the Cartesian form would be easier to draw. I'd be better at drawing than the other one. So for example, if I'm going to draw, actually just let me draw it right up here. So I've got 125 in the x, right? I've got negative 480 in the y, and then, or in the negative z, and then just ever so slightly in the y. So that that resultant force is down like this. And again, alpha goes from positive x-axis to the force, beta goes positive y-axis to the force, and gamma goes positive z-axis to the force. Okay, so that's where the 165, the 90.04, and the 75.4 degrees come from. Again, pretty challenging to visualize that way. I would rather leave it in the top one. So moving forward, you should understand those coordinate direction angles, but just know we won't use them a whole lot in future problems.